arithmetic instructions in PIC microcontroller. Okay, so first of all, let's see the PIC instruction set. We can see it from the data sheet. So if you go here and you see that instructions set summary, there is section 7 is instruction set summary. So if we click here, we'll find this is the set of instructions or assembly code we can use. There are 3 types of or categories of instruction set of PIC microcontroller. The first one is called byte-oriented file register operation, which means the instructions are affecting the whole byte, which is the whole 8-bit. Like for example, ADDWF or ANDWF. If you see that there is F means file, which indicates it's a register. It means that the ADDWF or ANDWF, it's affecting the whole register, the whole byte. There is another type called bit-oriented file register operations. These kind of instructions are affecting or are we can change the values of 1 bit of a register. As an example, we have bit BCF, bit clear file. It has 2 operands, F and B, which means clear the bit of number, for example, of number 5 or 6 of a register F. The third type of instructions are the literal and control operations, which basically they are used to introduce literal numbers, whether it's binary, hexa, or decimal, or even ASCII code. And some of these instructions are control operations, such as go to address certain address, or return from certain address to certain address, or retfee, return from interrupt, and ADDLW, which means return literal to W. These are control operations. So we have 3 types: the byte-oriented file register operations, which are affecting the whole register; the bit-oriented file register, which affecting a certain bit within a register; and there is the literal and control operations, which as we are use it for literals and to control the operations. Okay, so now we need to look at the instructions or arithmetic instructions. In PIC microcontrollers, we have only addition and subtraction, so we don't have multiplication. Simply because it's a risk, it has a risk approach, and there's only around 35 or 36 instructions. So it's a simple number of or few number of instructions. So if we would like to do a multiplication, you need to think of another way of doing it. So if you look at the addition, there are 2 types of addition. One instruction called ADDLW with an operand called K, which means it adds a literal K to W. In other words, it means W equal W plus K. The second one, ADDWF, which has 2 operands, F and D. D is the destination, which D can be 0 or 1. It says add W to F and put it either in F or in W. So if D equals 0, it will be W equal W plus F, or if D equal 1, it will be F equal W plus F. So if D equals 0, that means the destination is W, while if D equal 1, the destination is F. There is another type of instructions which is similar to addition, is called increment, which is basically we add 1 to the register. So it's increment F, which means in other way F equal F plus 1. Equivalent to these instructions, we have the subtraction. It's similar to addition, but it's subtraction. So we have SUBLW with an operand K, which means subtract W from literal K. In other way, it represents W equal K minus W. The other instruction is SUBWF with two operands F and D. It means subtract W from F, and if D equals 0, put the result into W. If D equal 1, put the result in F. So we have if D equals 0, W equal F minus W, or if D equal 1, F equal F minus W. Also we have decrement F, which means F equal F minus 1. So these are the 6 instructions we use in arithmetic instruction we use in PIC microcontroller. Just one thing here, that these instructions are affecting the status register, specifically the bit number 0 and bit number 1 and 2, which has carry, digit carry, and 0. So when in addition, when there is a carry at bit number 7, the carry flag will be 1, will be set. And if there is a carry from bit number 3 to bit number 4, digit carry will be 1, 0 bit. If the result is 0, it will be 1. If the result is 1 more than not 0, it will be 0. Opposite to that, the subtract instead of the carry, it will be borrow. It has similar way, but instead of having a carry, you will have a borrow. So if bit number 7 borrow a number from bit number 8, it means that there is the carry flag will be 1. If there is a borrow from bit number 4 to bit number 3, a digit carry will be 1. If the result is 0, the 0 flag will be 1. Okay, so these are the instructions. Let's do a simple exercise to show how to use these instructions. So let me just close the previous examples and let's go to create a new project, and next, so I will select F. Where is 16F? Yeah, so we are very close. 16F84A. Okay, use the same procedure. So let's call it arithmetic project. Finish. Okay, let's right click, assembly, let's call it arithmetic. Finish. First thing we need to do, as usual, is to include the PIC 16F84A.inc, and we need to have org 0 0 and end. Okay, so first thing we need to do is to define variables, and in order to do that we use a macro or directives, actually it's not a macro, called SUBLW. So SUBLW, we need to define the address for B16F84A. The best address is in the data memory is 20 hex, and we have NC. So it's a block where we can define the variables. So let's define two variables. One we call it constant 1 C1 and constant 2. So right now what will happen in the data memory, it will allocate two variables without being initialized in the data memory. Each one has an 8-bit. Okay, so let's now initialize this, the C1 and C2. We would say move LW decimal, let's do it as 10, and move WF to C1. Then we need to move LW, let's say decimal 7, and move WF into C2. Okay, so what we did right now is we had now, let's put a comment here. Now we initialize C1 to be equal 10, not minus 10, it should be 10, and C2 will equal 7. Okay, so we can now increment, for example, if C1, we can decrement if C2. Now let's clear W. So we put it like this way. Okay. Let me just do proper indentation. Okay, so what we did is we had C1 equal 10, C2 equal 7, then we increment C1. Now C1 would equal 11, and C2 will equal, because we decrement, now will be 6. Okay, now we clear W, which means that W equals 0. Let's do add LW, and we add W decimal. Let's do it as 5, which means W now is, it's actually W equal W plus 5, and since W is 0, so W equal 0 plus 5 equal 5. So now W is 5. Let's add WF. Let's add WF with C2, C1, and put the value into F, which means F equal F plus W. This leads to F is actually C1. Let's do it here, C1. C1. Now C1 equal C1 is now 10, 11 now right now, plus W, which is 5. That means C1 is now 16. Okay, so we did the increment, the decrement, addition. Now let's do the subtraction. Let's subtract a sub LW. Now W has 5. Let's subtract with W equal 3 or 2, 3. Now, no. Let's do it as 9. Now that means is W equal 9 minus W. This leads to W equal 9 minus 5 equal 4. So now W would equal to as 4. The last instruction we'll use is SUBWF. SUBWF. Let's do it with C2, which means comma. Let's do it here now. W. Now W equal subtract C2 from W, so it would be equal me see, just give me a sec. So the subtract W from F, which means F minus W. Okay. Which means C2, since C2 equal to the last value C2 was 6, so it would be equal 6 minus W equal 4. Sorry, 4. Even now the new value of W equal 2. Okay, so let's give it a try now. Let's just build it and see if there is any problems or any bugs. Okay, there are 2 errors here right now. Oh, there are many errors. Let me see. Oh, yeah, should be end C. Okay. Now it should be good now. Okay. So now it's working. Now in order to define the variable C1 and C2, we need to go. Okay, so now we need to see the output. It's a bit tricky. First of all, we can see the output of the W register from the variables. So if we go to the W register, okay, so this will show W register, and let's just run it and see, and then we need to pause it, pause and reset. Okay, so we have the initial value, decimal, and the hexadecimal and the binary. Now Previously, in the old versions of MBLab, we used to see the constants where we define it in the variables view. But right now, recently, it's really impossible. So if you try to add C1 as global symbols into the variables, it will not show up. So probably the easiest way and the better way is to see it from other view, so we can see it from the file register. Okay, so this is the file register. No, not the file register, give me a sec. So we can see it from SFR. Yeah, so we can see it from the SFR. No, file register. Yeah, if you see the file registers, it has at the top it shows the special function register, and at the bottom you see the general purpose registers. So if you notice that our C block is defined at 20 hexa, so if we look at the address of 20 hexa, it will show these are C1 and C2 at 20 and 21 hexa. So initially, like C1 will change here and C2 will change there. So if this is the values you see here, it's just any random values, previous old values, so we don't care about them. So now let's start and press on F7 and see how C1 and C2 will change. So now C1 becomes 10 because we move value of WF value, literal value 10 into C1. Now C2 will be 7 if you look here at address number 21. See, now C2 is 7. Now if we increment C1, this will be 11, and decrement C2, this will be 6. Good. Okay, this is 6 and this is 11. Let's see the W register. W contains now 7 because we already moved value 7 into W in this instruction, move LW. Now we can clear W, it will be 0. See, W now is 0. We see it from the variables. If you get back, now we add LW to 5. There's literal 5. Let's press. Let's go to. Give me a sec. Put this here and the variables here. Okay. Yeah. Now let's see W. Press F7. See, now W has 5. Now we need to add C1 number 5. So if we add 5, this will see 5 plus 11. This will be 16. Now we subtract 9 minus W, which is 5. The W will be 4 now. If we check variable, now 4. Now if we subtract WFC2 comma W, now W will be 2. Wow, why? W was 2. yeah, no, should be W5 here. W equal 4. Let's do it again. 7. Clear W. W5. 5. W4. C2 should equal to 6. 6 minus 4. So W should equal to 2. Anyway, it seems that there's something problem here, because let's just put an instruction called NOP. Just an instruction I need to see, and let's run it again. Okay. Okay, so let's see W again. Just need to check W. So W was 7, then clear W become 0, then we add 5 W, then W doesn't change here, then 9 minus 5 W equal 4, then 6 minus 4 W equal 2. See? Yeah. Basically, because we went to the end and so it clears W. So when you introduce NOP as an extra instruction, we have this subtraction. So if you click here now, W will be 0. Okay, so I hope it's clear right now. That's for today.